This is IAT814 Visual Analytics, lecture number 2, in which we talk about frequency tables and histograms. So frequency analysis is another type of descriptive statistic. And the reason why we're interested in this, and we'd actually used one in the previous lecture segment, is a frequency distribution presents the counts of observations grouped within pre-specified groups. Relative frequency distribution presents the corresponding proportions within the groups. And we all have kind of experience of seeing these in the popular press while reporting quantitative values. So here are some examples on the right. 40% of respondents are male, and this second example, 60% of younger voters cast their vote for Trudeau compared to 52% of voters over 50. In the second example, there are two sets of categorizations going on, or groupings going on. One is the non-overlapping sequence of age ranges, young, whatever that means, presumably one or two categories of middle-aged voters and voters over 50. And the second is what party or what politician they voted for. So to build a frequency analysis, what you need to do is put together a frequency table. And a frequency table is a sequence of bins, what's called bins or buckets, that are labels for categories of data. And typically, given the kind of data that you've got, in this case, this is integer variables here, you create categories or bins or buckets that are numerical in nature in this case. So we have the data that is whose value is 0 through 50. There are 3 of those. Values 51 through 60. There are 2 of those, etc., etc. All values above 90 fall into this bucket, which means greater than 90. And so here's the table, and here is the visual histogram that you see as a result of plotting out that table. So a histogram is something where you get to see what's going on in the data. And of course, what we do is we draw this histogram by splitting the data range into equal-sized bins and count the number of points from that data set that fall into the bin. Now, the little exception is values at the lowest end and the highest end might also take any value that's less than the minimum and any value that's greater than the maximum, just to catch any things that are big outliers. And typically the way you see it plotted is that the vertical axis is the frequency or counts of the data that you've got. Counts if it's a frequency table, relative frequency table when you're using proportions. And the horizontal axis is the binned variable. And here we have a data set with very, very small bins. Roughly 0.02 is the bin size here. We often use ordered bins, particularly if the data is not nominal. We showed an example in the previous segment where the data was nominal. It was cars, trains, bus, etc., that kind of thing. But the examples we've been showing here, the data is at least ordinal or perhaps numeric. And kind of what this a histogram does is it turns the data into categories. Now, in this case, the categories are kind of categories of value, but there's this kind of transformation that's going on to quantize the data and its counts into these sequence of non-overlapping counts. So the histogram, the reason why you do it, is it graphically shows a number of things that you may be interested in your data set. The first thing that we list here is that it shows the centrality, if there is one, of the data. So here in this histogram, we see that the central tendency of this data set is here, 299.9 or something like that. We can see that the range or spread is also shown from roughly 299.6 to 300.1 roughly. It can also show the skewness, and we'll talk more about what that means later on in this segment. And it will also show outliers. So given that you've got a centrality idea represented visually and a spread, you get an idea of what the overall behavior of the data, and outliers are exceptions to that. Typically that lie well outside of the kind of the standard range, either positive or negative with univariate data like this. The other thing they show that it's very important is the mode or modes singular or plural in the data. This data has only one mode, but there might be more than one mode, and we'll show examples of that later on. So to discover centrality, visualization can help indicate what centrality measure to use. So plotting a histogram can be useful to give you an idea of what the most useful centrality measure is. And we showed an example in one of the later slides in lecture 3.1. So if the data is unimodal, as this data set is, meaning having one central point, and symmetric, meaning roughly the same number of data points to the left of the central mode of the single mode as the number to the right, then we can say the data is symmetric, and it certainly looks symmetric about this central point. In that case, you should use the mean. This example here shows a skewed data set in which it is unimodal, just as before, but you can see that the mode of this data is somewhat to the left of the kind of middle value of the range. Not that that has any direct meaning here, but 230 minus 160 ought to put you somewhere around here, or 190, and that's not where the mode is. That's right here at 180. And so what that means is that this thing is skewed. There's probably more data points to the right, and also the range from the mode to the right is greater than it is from the mode to the left. In this case, the centrality measure to use is the median. So because histograms quickly show distribution clusters, it can also be used to show if you have a distribution that's bimodal. So here is a data set with two modes, one here and one here. And you can really tell that because there's a very strong peak at this location, very strong peak here, with a significant enough separation between those two, what you can fairly call clusters in the data. If there was a bin or two that had a count of 0, then that would be a very strong indicator of bimodal distribution. But colloquially, we would call this as an example of a bimodal distribution. And in that case, if you have something that looks like this, you can't really use a centrality measure like median or mode, because it'll just completely mislead you as to what's going on in the data. The mean or mode, the mean and the median will both give you values around here, and that's not what's going on in this data set. You may also have more than two modes. In this case, this is a data set that has 3 modes, one here, here, and here, and each of these clusters is roughly symmetric, with the small counts at 160 and somewhat larger counts at 190. And in this case, once again, there's no separate single central tendency. There's in fact 3. That's what it looks like in this data. And you can't assume that there are any central tendencies like median or mode that are actually meaningful in this, because you can see this thing has, in fact, 3 modes. So when you're building histograms, one of the things that can be a little bit tricky is to come up with a bin size that makes sense for the data. And to some degree, the bin size ought to be chosen on the basis of the number of data elements that you have. With a small quantity of data, then having too many bin sizes ends up misleading you as to what's going on with the data. And it can't be too small, as it's shown here, and it can't be too large, as it's indicated here. The small thing just basically isn't doing a histogram. It's doing, it's a kind of a degenerate histogram. This thing's also degenerate because it's smushing all the data together into 3 categories. You might see this if somebody was trying to mislead you as to what's going on in the data. This third one looks a little bit better, and it's also reasonably sensible. There's roughly 3 bins per unit here. So from 1.5 to 2.5, 2.5 to 3.5. The bin size is a little bit less than 1/3. In this case, it's probably 0.3. So the issues that come up with histograms, as in addition to the one I just shown you about choosing the proper bin size, is that for small data sets, histograms can be a little bit misleading. Small changes in the data or in the bin boundaries can result in very different histograms. And it's not, in some sense, it's not the histogram's fault, as it were. The problem really is that when you're trying to histogram a small data set, you're inviting trouble. It's like using a screwdriver in place of a hammer to pound in a nail. It's not the right tool for the job. For large data sets, histograms can be quite effective at illustrating the general properties of the distribution. However, histograms really only work with one variable at a time. We've been showing in these past examples, univariate data. There's a single column of data, and we're just simply plotting the counts of items in the non-overlapping bins. It's a little bit difficult to extend to 2 dimensions. The example of voting an age of voters and voting for Trudeau or not is an example of that, but you would have to use a repeated number of histograms for that. And it's really not possible for greater than 2 dimensions to use single histograms. So histograms tell us nothing about the relationships amongst variables. You might use a histogram in order to infer that something is going on, but it's not depicting interesting things going on directly, because what will happen is that if you have a multi-dimensional data set and you do a histogram of one of the dimensions, what might be happening is that you're getting a number of behaviors kind of building up upon a single dimension. Typically, what you want to do for higher dimension data is to do scatter plots or clusters. Okay, so that's it for frequency tables and histograms, and that's the end of lecture 3.2.